Okay, welcome. We're going to look at a little bit of a review for what we did in class with our spaghetti bridge lab. We talked about dependent and independent variables, controls and constants. For our spaghetti bridge, we said that our independent variable, what we were controlling was the number of strands of spaghetti, which is going to go on our x-axis by default. And on our y-axis, the dependent variable, the number of pennies, which was representative of the weight that the bridge could hold, that's going to go on our y. And so we investigated the relationship between the number of pennies or the weight with respect to, or as a function of, the number of spaghetti strands we used. I've got some made-up data over here in this data table. Recall that we are going to use a data table anytime we record data. Keep it nice and organized. I saw many groups doing a fantastic job of having nice, clean, organized data tables, and that is fantastic. We want to make sure that we record it, and if we have it on our whiteboards, we're taking a picture, writing it down in our notebooks, whatever, so that when we are doing our analysis, we can easily get back to our data. We also want to make annotations while we're collecting data. I saw some of that, which is great. If you notice something that's off or strange, or if someone bumps your table while you're doing an experiment and something changes the result a little bit, you can make a note of that, and that's an important thing to include in a conclusion or in your results. So we're just going to very briefly kind of show what we mean by finding a line of best fit. I got my ruler here. It's a nice, clear, transparent ruler, and I had some made-up data, and I'm just going to sprinkle that data into my graph. And I haven't spent the time to scale my graph appropriately, which is what I will need to do anytime I do make my graph. I want to 1, 2, 3, 4, 5, 6. Let's get a couple more data points. I'm going to put one down here. So this could be any sort of data, not just from our spaghetti bridge. This could be any sort of data. Let's put one more data point there. Okay. And I'm just going to use this as an example for drawing our line of best fit. Remember, this is our y-axis up here, and we, by default, have our dependent variable was measured up. And down here I have my x, which by default I have my independent variable. This is not always the case that you put independent and dependent on these axes. It's just kind of the basic convention. And sometimes you don't. Sometimes we're not even graphing a relationship between independent and dependent variables. We could be graphing some other relationship, as we will see. But here's just our example. We want to make sure that we would space out. If I have 2, if this is 1, 2, 3, notice I have the same spacing, 2 squares for every integer I'm writing down. And then on my y, this is my 0, 0 origin right here, where I use these two more thick black lines to indicate my axes. Then if I'm scaling up by 1, 2, 3, maybe by 4s, maybe this is 10, 1, 2, 3, 4, and this is 20, 1, 2, 3, 4. You get the idea. I want to make sure I'm appropriately scaling the graph. Okay. When we go in to draw our line of best fit with the ruler, I can adjust my slope and y-intercept by moving my ruler like this. I change where it crosses over the y-axis, and when I rotate, if it'll let me, my ruler, I change my slope. And the general rule, like the one we'll follow if we're doing this manually with our ruler, is get the same number of dots or data points above your ruler line as there are below it. So I'm going to use the centimeter ruler mark to find a place where the equal number of dots are above and below, and I want to try to fit the data the best. I don't want to force it through the origin. I do not force my line of best fit through the origin. That's the origin down there. So I'm not going to make my ruler go through that, because sometimes it shouldn't. I'm also not going to force it to go through any particular data point. It's fine if it doesn't touch any data points. That's fine. It's just trying to fit the data the best. So I have 1, 2, 3, 4, 5, 6, 7, 8 data points. So actually right now I have 4 data points above and 4 below my ruler line where my centimeters are. And I could change it to get it to be a better fit. That looks not bad actually, like that. So in pink I'm going to draw what is now my line of best fit. As soon as I have that line of best fit, my data is done. This line is now all important and the most important thing. And it's going to describe the trend in my data. Notice I have a y-intercept that is not 0. Okay. I also have an x-intercept over here somewhere that is also not 0. And that may indicate error. If I think about my situation physically for my spaghetti strands and pennies, when I have 0 strands of spaghetti, I should have 0 pennies supported by that non-existent bridge. So in that case from our lab, the line of best fit should go through the origin. If it doesn't, and it probably doesn't because we have some error and we're drawing a line of best fit, then the y-intercept indicates to me a little bit of error I have in my mathematical model. And this happens, okay? So we just want to take note of when it does and whether it should or not intercept the origin. So here we have 4 data points above and below my line. When I come up with the mathematical model at this point for my investigation, I have a linear fit, which means I have a linear equation that describes that line. Y is on my y-axis. That's my number of pennies for our lab investigation this week. And I have x, which is the number of strands of spaghetti. Number of strands spaghetti. I have my y-intercept, which is my b. So let's pretend that this is, I'm just going to say it's 12. No, that doesn't make any sense. This is 10 right here. So halfway is 2, so that's 5. And so a little more than 2.5. So I'll say it's 2.7. Let's say my y-intercept is 2.7. I'm just estimating where the y-intercept is right here. Okay, and then I have this last guy I need to figure out, and that is our slope. Often our slope will represent something really important, and we can use that to figure out things about our natural universe based on the line of best fit that we've created from the actual data we've collected from a real experiment. So we need to remind ourselves how we find this m, this slope. So m is our slope. It is our change in y, or y2, like the second y minus the first y, divided by x2 minus x1. And we can also write that as delta y divided by delta x. And when we do that on our line of best fit, we want to find a point that, like this one right here, crosses over both grid lines really well. So like, here's another one right there. So this could be my x1, that doesn't look like x1, but that would be my x1, y1 right here, and my x2, y2 right there. So we can calculate the slope real quick for this, and then we'll be good to go with our mathematical model. So this is our change in y divided by our change in x. So here's x2, y2. And this point is x1, comma, y1. So let's find out what these are. Here x is 6 and 20. So this is right here. This one's actually 6, comma, 20 are its coordinates. And this one down here is 1.5. Even though we can't have 1.5 spaghetti strands, we're no longer looking at our data points or the specific spaghetti strands. We're looking at what equation describes this line. And then this guy right here is 7.5. 7.5, because this is halfway and this is 5, and this is a quarter of the way to 10, which is 2.5. Okay, so 7.5. So this coordinate is 1.5, comma, 7.5. X, Y, X, Y. So y2, there's y2 is 20 and y1 is 7.5. So there's y2 is 20 minus y1, 7.5, divided by x2, which is 6, minus x1, which is 1.5. So I have now, let's erase and get some space to get our full slope finally. I have, come on, pen. 20 minus 7.5 is 12.5, right? Divided by 6 minus 1.5 is 4.5. So then we can pull up this guy if I want. My calculator, which I know we all have, 12.5, and we'll remember to bring to class, divided by 4.5 gives me a slope of 2.78. I round it 2.78. Okay, 2.78. So that means for every one I go over on the x, I go up 2.78. Okay, and this slope now can be substituted into our, here's the slope that I have, 2.78. That can be substituted into our m. So if I want to make a prediction about my y value in my linear equation, this is the equation I'm looking at, how many pennies are going to be held if I have X amount of spaghetti strands? Well, I can make that prediction because I know m is 2.78. That's my slope. I know that value now. Check mark. X, let's say I want to know how many pennies are held with 100 spaghetti strands. Well, I substitute 100 in there. Plus B, my y-intercept modifies my line a little bit and describes my mathematical model. So plus 2.7, well, I can get a value, right? Y would be 2.78 times 100, which would be 278, plus 2.7. So 270 or 280.7 would be what my y is equal to. So this is all an example with made-up data I just grabbed, but the pink line of best fit is when we make it manually, we want to make sure we have about equal number of data points above and below that line, and it goes right through the data. It's okay if it doesn't hit the dots. It's okay if it doesn't go through the origin. Okay, we're just trying to describe the trend of the data. And then we want to make sure that we can find the slope m and express that in a linear equation so we can use it. There's our slope m and there's our linear equation so that we can make predictions when we change something like the number of spaghetti strands. We want to be able to do that when we make predictions about projectiles that we might launch or roll off the table, or other labs that we'll do. We'll find a mathematical model. We'll find a linear equation that describes some line that is a model for our data, and then we'll use that equation to make a prediction of where something might land if we launch it, for instance. Okay, so there's our quick review for what we've been doing. Data collecting from labs goes in our data tables. We represent it visually on our graph. We use a line of best fit that we will end up using computers to help us figure out quickly, but we need to be able to do it manually as well. And then we use our slope equation to find our slope and create our linear equation for our line of best fit that we can use for making predictions. That's all for today. See you next time.